Today I'm going to explain a research paper titled Hybrid Renewable Energy System Design, a machine learning approach for optimal sizing with net metering costs. This study focuses on how artificial intelligence can help us design smarter, more cost-effective renewable energy systems. As the world transitions away from fossil fuels, renewable energy sources like solar power are becoming increasingly important. However, one major challenge with renewables is variability. Solar energy depends on weather conditions, time of day, and seasonal changes. Because of this uncertainty, designing a reliable and economical energy system becomes quite complex. If we under-design the system, it won't meet demand. If we over-design it, the cost becomes unnecessarily high. This is where hybrid renewable energy systems come in. A hybrid system typically combines solar panels, battery storage, and a connection to the electrical grid. The grid acts as backup when renewable generation is insufficient, and in some cases, excess electricity can be sold back to the grid through a policy called net metering. However, net metering involves costs and pricing structures that significantly affect system economics. Therefore, determining the optimal number of solar panels, batteries, and inverters is a critical design decision. Traditionally, system sizing is performed using historical data from just one typical year. But the problem is that weather patterns and electricity demand change over time. Designing a 20-year system based on a single year of data can lead to inaccurate results. The key contribution of this paper is that it moves beyond the one-year assumption and instead uses long-term forecasting combined with advanced optimization techniques. The researchers developed a data-driven framework that integrates machine learning models with hybrid metaheuristic optimization algorithms. First, they used advanced machine learning techniques such as CatBoost, LightGBM, and XGBoost to predict solar radiation, temperature, and electricity demand over a 15-year period. These models were trained on historical data to generate accurate hourly forecasts. This step is important because it creates a more realistic representation of how renewable generation and load demand will evolve in the future. Once the long-term predictions were generated, the second step was optimization. The researchers applied 9 different hybrid metaheuristic algorithms to determine the optimal system configuration. These algorithms are inspired by natural processes and intelligent search mechanisms. Their objective was to minimize the total net present cost of the system while ensuring reliable energy supply. The cost function included capital costs, operational costs, battery replacement, grid purchases, and net metering revenues. By combining long-term forecasting with intelligent optimization, the framework evaluates system performance over its entire lifetime rather than a single year. This provides a more robust and economically sound design. The results of the study are very interesting. The system designed using 15-year forecasted data was more reliable and economically optimized compared to systems designed using only 1 year of data. Among the tested algorithms, certain hybrid metaheuristic methods performed better in finding lower-cost solutions. In the specific case study presented in the paper, the optimal configuration included 305 solar panels, 21 batteries, and 10 inverters, with a total system cost of approximately $1.46 million. This configuration successfully balanced economic performance, reliability, and environmental sustainability. One important takeaway from this research is that long-term variability matters. Energy systems are long-term investments, so the design must account for future uncertainties. By incorporating machine learning forecasts, planners can better anticipate changes in solar generation and electricity demand. By combining this with advanced optimization algorithms, they can identify cost-effective and sustainable configurations. In simple terms, this paper demonstrates that artificial intelligence can significantly improve renewable energy system planning. Instead of relying on simplified assumptions, we can use predictive analytics and smart optimization to design systems that are more realistic, more reliable, and more economical. This approach is especially important for countries investing heavily in distributed renewable systems and net metering policies. It provides a practical framework that energy planners, engineers, and policymakers can use to make better decisions. Overall, the study represents a strong step toward intelligent, data-driven renewable energy system design, combining machine learning and optimization to support the global transition toward clean and sustainable energy.